Good morning, everybody. Thank you for coming to EAG Laboratories Coffee and Conversations with EAG Experts. My name is John Mosquito, and I'll be your MC through the hour here that we're going to be spending talking about materials identification. Now, today's agenda, I'm going to give you an introduction to Eurofins EAG Laboratories, talking about who we are, what we do, and how we can help you with your analyses. We're going to talk about materials identification. In this talk, we really want to have a conversation with you. And when we have a conversation, we're going to talk about materials, we're going to talk about identification, and we're going to talk about materials identification. And for each person, you're going to have a different idea of what that means. And because we only have an hour to spend with you here today, we're going to shrink down that conversation to 3 different groups. We're going to talk about thin films. We're going to talk about techniques for materials identification of organics. So maybe longer molecules as opposed to thin films, where we're typically looking at simple structures, elemental analysis, organics, longer range order, molecules. And then third, the XRD, we're looking at phase, so even longer range structures, right? So not going to cover all the different types of materials identification that we can offer through EAG Laboratories, but we're going to give you a snippet based upon these 3 categories. And then we're going to have conversations and questions with our experts. So you'll be able to have a question and answer period afterwards. And then if you want, we can have individual meetings and individual conversations to talk specifically about your needs and your types of analysis that you would like to cover. And then obviously we'll have a tour of EAG Laboratories here in Sunnyvale, California. So, introduction to EAG. EAG has over 45 years of experience in materials testing services. We started here in the San Francisco Bay Area in San Carlos, where we started specifically looking at the dopants in semiconductors using SIMS, secondary ion mass spectrometers. We have grown that business to include many, many different techniques, focus on semiconductor, but also across the industries that are here, both here in California, in Silicon Valley, but across the world. So we now support semiconductors, semiconductor manufacturers, medical device, automotive, purity services, aerospace and defense, and many others. And I'll give you some more examples as we continue through our introductory slides here. We are a service lab. We support clients, 5,000 clients in 20 different facilities located within the United States, Europe, and in Asia. We're IP secured, ITAR certified, and are accredited and certified across multiple industries and markets. We are also owned by Eurofins. This is a large conglomerate of labs. We are a lab-based business. So our parent company is a multi-billion-dollar global leader in scientific services and allows us to grow with you, to bring in the tools and the techniques and the expertise that you need to solve your problems also. EAG Laboratories is across the world. Located here, we have 5 active labs here in the San Francisco Bay Area, 2 more down in Southern California, Arizona, St. Louis, the East Coast, and across in also Europe and in Asia. We have a 6th lab coming up in California, based here in Sunnyvale. That's going to be our new battery lab, where we'll be doing battery materials characterization. Now, I spoke already about the diverse range of industries that we serve, but here's a list of all of them that we do: semiconductor devices, semiconductor equipment, consumer electronics, aerospace and defense, automotive, medical device, chemicals, and across the board, including litigations and energy, telecom, raw materials. So anytime you need to know about your materials, EAG has the techniques and the expertise to be able to help you answer your questions. We serve the entire life cycle, from research and development to product innovation, troubleshooting, quality assurance, manufacturing support, failure analysis, regulatory, supply chain control, and litigation. So wherever you may need us, we are here to help you solve your issues and help you grow your business. Now here's a SMART chart, formerly called the bubble chart. SMART stands for spectroscopy, microscopy, analytical resolution tool. Really what it is a way to visualize the different techniques that we're going to talk about today and all of the other techniques that EAG offers, in all of our laboratories. So within the box, we have on the x-axis analytical spot size, ranging on the right-hand side from very large to centimeter size, then going from right to left down to millimeters, down to microns, down to nanometers, even into the angstrom. So depending upon the size of analysis, and usually you would normally think about that as how large of an area. Here it really means how small of an area can you analyze exclusively to be able to get chemical information, get molecular information, to get size and elemental compositional information. This is the spot size down on the lower x-axis. On the y-axis is composition or concentration. So at the top of the list, we see percent levels of concentration, and we see many different techniques up there that can give you concentrations at percent levels. Then as we go down into sub percent levels, down into the ppm levels, into the ppb levels, and even into the parts per trillion levels, we have techniques that will be able to give you that composition at those ranges within those spot sizes there within the box. And then we also have techniques outside of the box. On the right-hand side are our bulk techniques, which are concentrated at the near surface, will give you a bulk composition, again, at the different concentration levels that you may need. And then also the imaging techniques at the bottom of the box. And these will give you a picture or a look at your material, literally a look at your material, whether it's going to be as an electron beam image or an X-ray image or a roughness image, to give you that information that not beyond chemical composition. Now, many of these techniques can do materials identification, and some of them can't. But we're going to talk about a few that can. And what we mean by materials identification is it's able to do an analysis and discover what's present. So you don't have to put in the elements you're looking for, you can discover what's there. That's really what materials identification means in our view. And that's how we're going to concentrate our talk to the techniques that can discover what is there and give you that identification. What we're also looking at is depth of analysis. For all those techniques, there's a sweet spot in depth, whether it's the first few atomic layers, like in time-of-flight SIMS, Auger, and XPS, or more into thicker films, into the nanometer or even micron thick films, or then into the bulk. And as we go from left to right, we can see the techniques laid out in depth of analysis. So we can take advantage of that. So depending upon what you're trying to look at, whether it's a surface contamination to identify, a film composition to identify, a bulk to identify, we can choose the right technique to give you that sweet spot, to give you the best data possible. With that, I would like to introduce you to Dr. Monica Neuberger. She's the manager of our surface analysis group here in Sunnyvale, California, and she'll be talking about thin films. Thank you very much, and I look forward to speaking with you as we go through the rest of our conversation here.
Well, thank you, John. I'm Monica Neuberger. I'm the manager of the Surface Science Group here at EAG's lab in Sunnyvale, California. I've been with the company for almost 20 years, working primarily in time-of-flight SIMS and XPS. I'll be talking about those two techniques as well as Auger analysis, and I'll start with Rutherford backscattering. Of the techniques that I will be discussing, this is the least surface sensitive. It probes several hundred nanometers into a sample surface. With Rutherford backscattering, we hit a sample with alpha particles. These are helium nuclei, and when these hit the sample, they recoil with an energy loss. We measure the energies of these backscattered particles, and this tells us the mass that the particle hit, how much of it there is, and the depth distribution of the element with that mass in the analyzed volume. RBS is wonderful for determining the composition and thickness of thin films with very high accuracy. It is also good for measuring the density of such films if one has a good measurement of thickness. RBS essentially gives a depth profile completely non-destructively. Its accuracy is very good. It is quantitative, but does not require a reference standard. RBS is actually used to develop reference standards for several other techniques. Hydrogen can be a difficult element to measure by many techniques, but RBS is quite good in a hydrogen forward scattering experiment. It can give a nice accurate measure of hydrogen content, and RBS can analyze insulating samples as well as conductors. I have a brief example of RBS data. This is its analysis of a silicon nitride film. In the RBS spectrum, we can see a difference between the silicon within the film compared to the silicon of the substrate. So we get a measurement of each, the silicon and the nitrogen. The hydrogen is measured in a separate experiment, a hydrogen forward scattering experiment. And then the two data sets are combined to produce the overall composition of the film. So this is wonderful for, things, as I said, several hundreds of nanometers thick. Sometimes one needs something much more surface sensitive. In this case, working ever more surface sensitive within, the techniques I'm discussing, we have X-ray photoelectron spectroscopy. This will probe the top 5 to 10 nanometers of a sample surface. Within XPS, we hit a sample with an X-ray beam, and this causes electrons to be ejected. The energies of these electrons are characteristic of the elements they came from. So XPS can be very good at determining not only the composition, but also the chemical bonding environment of organic and inorganic materials. If it is combined with sputtering steps, energetic ion sputtering, we can give a depth profile for an in-depth composition of a thin film. I mentioned XPS can give bonding information as well as the composition that comes from the really precise energies of the electrons being ejected from a surface. XPS is semi-quantitative. It will give composition in terms of atomic percent, but it does use sensitivity factors. All of these concentrations are based off various standards, and the sensitivity factors are supplied to us by the instrument manufacturers. I mentioned the depth profiles. I have an example of XPS data here. This is analysis of a stainless steel stent. In this case, the analysis area was many tens of microns in size. From an XPS standpoint, this is a very small lateral area to analyze. XPS is normally analyzing many hundreds of microns laterally at once. But still, from this small area of this stainless steel stent, XPS is showing the difference between metallic iron and iron oxides, metallic chromium and chromium oxides. In the carbon spectra, we can see various carbon functionalities, hydrocarbons and carbon oxygen functionalities. When one needs even a smaller lateral area to be analyzed, if one perhaps has particles, defects, bond pads, Auger electron spectroscopy is wonderful. The principle of operation for Auger is very similar to XPS, except the sample is being hit with electrons instead of X-rays. It's a somewhat different process causing electrons to be ejected, but still the energies of these electrons are characteristic of the element they came from. Because electrons can be focused to a much smaller lateral area than X-rays, Auger is particularly useful for analyzing defects, particles, small areas such as bond pads or traces, things of that sort. Auger is a bit more surface sensitive than XPS. It probes roughly the top 3 to 5 nanometers of a sample surface. I mentioned it's a very small spot size, can analyze very tiny particles. Like XPS, it is semi-quantitative because it uses sensitivity factors, and like XPS, it can be used in a depth profile mode. Because Auger is coming in with electrons and electrons coming out, Auger is best used for electrically conductive materials. It does not analyze insulators very well. But I have a lovely example of Auger data here. We're looking at these dendritic features on a metal alloy. Auger produces an SEM-like image within its instrument, which helps an operator select very precise areas for analysis. In this case, we can see the 2 areas on this dendrite feature had high levels of sodium compared to a region off the dendrite. Auger can also produce chemical maps, so we can see in this map of sodium that the sodium is all over that feature and not in the outlying area. Auger will give wonderful elemental information, but it does not give the same kind of bonding information as XPS. It will not differentiate an oxide from a metallic form, and it's not very good for analyzing organic species. It will detect carbon, but not the compound carbon came from. So for the combination of organic functionality, organic identification, and small spot size, time of flight, secondary ion mass spectrometry can be an excellent choice. It's very good for analyzing the surface of both organic and inorganic materials. It will produce, it will identify molecular fragments and elemental species on a sample surface. That's what we've tried to depict in this cartoon here. In time-of-flight SIMS, we hit this sample with a pulsed primary ion beam, and that causes species to be desorbed from the surface. We measure the time it takes all of these ions to fly to the detector, and then convert that time to mass. TOF-SIMS is extremely surface sensitive, probing only the top 1 to 3 nanometers of the sample surface. It has very high mass resolution, which allows for the positive identification of mass fragments. Like Auger, TOF can also produce chemical maps of a sample surface. And in some cases, we can provide depth profiles of organic materials and while keeping the organic information intact. We do not destroy organic molecules and turn them into a pile of carbon atoms. I have a brief example of time-of-flight SIMS data. Our pulsed primary ion beam is rastered over a sample surface. That the instrument produces a mass spectrum combined over that complete area. And after the analysis is finished, we could select particular masses if needed and produce maps based on each individual mass fragment. These could be a map of elements or a map of molecular ions. We also get a total ion image for that area. In all of these images, bright colors indicate a high yield of ions and dark colors are few ions. From a total ion image, we could select areas and see how the species present in one area might be different from all of the species present in a different region of the sample. I've highlighted one region to show the very high mass resolution of time-of-flight SIMS. All of the peaks in this region all have the same nominal mass of 59, and yet the element cobalt is very clearly resolved from a number of molecular fragments. There are some very common questions that we get for all of these techniques, such as, if you want to analyze an organic residue, what technique should you use? Well, TOF-SIMS is wonderful. TOF can also analyze insulating materials. RBS, very good for finding density of a thin film. Hazes, what technique would we recommend to analyze a haze? Well, hazes can come from many sources. XPS, Auger, and time-of-flight SIMS are all excellent, but there are others. But when we come back to this idea of an organic residue and what technique should be used, yes, time-of-flight SIMS is wonderful for very thin residues, trace level species. If the residue is thicker or there is perhaps more of it present, FTIR is wonderful, so is Raman, so is nano IR. And these techniques will all be explained to you by our next presenter, my colleague, Dr. Janneke Schneider.
Thank you so much, Monica. So hi, everybody. My name is Janneke Schneider, and I will focus today on identifying organic materials. So with respect to techniques that we use for identification, we have spectroscopic techniques and chromatographic techniques. So spectroscopic techniques, they're looking with a microscope at a specific area, and these techniques include FTIR, Raman, and nano IR. So on our smart chart, you can see where they're located. So nano IR has the smallest spot size, and Raman is next, and then FTIR is after that. NMR is a spectroscopic technique, but it's a bulk technique, so it's not a spot size. And that's also true for the chromatographic techniques, such as GCMS and LCMS. I also want to say a word about information depth. So again, nano IR is probing right at the very top of the surface, going maybe 100 nanometers into the surface, while FTIR and Raman are going to probe much deeper, going about a micron into the surface. Okay, so how do we do this identification? So the principle behind identification is called molecular fingerprinting. The idea here is when we analyze the sample, typically we are irradiating it with some kind of light, and then we're getting a spectrum back. And this spectrum that we obtain has to do with the functional groups that are present in the material we're analyzing. So you can think of this as a fingerprint for all the species that are present. Here's an example of an ABS acrylic polymer, and we see that it has a nitrile functionality at 2237 wave number. It has an ester at 1722, ether at 1247, and so on and so forth. So these various peaks represent functional groups, and this collection of functional groups is what creates this fingerprint. And we use this fingerprint to identify small molecules, polymers, thin films. We can also use it for certain inorganic molecules, but this is really a organic technique, right? So I'm going to use one example, kind of a simple example to illustrate this idea. So we are going to be analyzing this green drape material. And when we do FTIR on it, we're going to figure out that, look, it actually matches very well to material called Creighton. Creighton is a styrene, ethylene, butylene styrene. So it's a terpolymer called SEBS. And so with FTIR, we're able to identify the base polymer. Now, when we do Raman on that same exact material, we are not going to see that base polymer, even though the two techniques are using the same kind of principle. What we'll actually see when we do Raman analysis is we're going to detect a copper phthalocyanide dye called histosol green GK. So this is the structure. So FTIR is going to see the base polymer, Raman is going to see the dye. Now, if we do GCMS on this, my next slide, we're going to see something completely different yet. So with GCMS, we would take a little piece of this fabric, this drape material, do an extraction on it, and then inject it into our GC. And then this is our total ion chromatograph, so you can see the series of peaks. And what do we find in it? We find various lubricant or processing aids, as well as plasticizers. So now you can see how 3 techniques aimed at one material can be very useful for identifying different components of it. And generally speaking, when we compare these 3 techniques, we can see that they excel for certain characterization and are not as good for others. And there's kind of a guiding principle for it. So comparing FTIR and Raman, FTIR is very sensitive to molecules that have a dipole, that have electron density being pulled away. So in this example, we have ethyl acrylate, right, which has this carbonyl. This carbonyl has a strong dipole, and that is why this molecule is going to have a very strong peak in FTIR, but a more muted peak in Raman. And that's because Raman is much more sensitive to symmetry. So not a dipole, but more symmetrical bonding. And in this case, we have this double bond here. So this has great symmetry, and that's why you see it much more strongly in the Raman, while in the FTIR, it's relatively weak. Okay, so if we look at this table, we can see that carbonyls are going to be strong in the FTIR, but weak in the Raman, and the opposite is true for the double and triple bonds. They're going to be very strong in the Raman. In addition, diatomic molecules like iodine is not going to be observed by FTIR, but they will shine up brightly in the Raman. This is also true for benzene rings. Okay, now GCMS is quite good at detecting carbonyls and double bonds and triple bonds, and even some diatomic molecules. Where GCMS is not going to be successful is looking at larger molecules, looking at polymers or inorganic compounds. And you can see polymers and small molecules can be easily detected by IR, FTIR, and Raman, but not GCMS. GCMS can only do small molecules. And really anything smaller than 800 gram per mole for its molecular weight. In addition, none of these techniques can detect any metals. And with the inorganics, FTIR can and Raman can do some, and I'll talk about that in just a second. I also want to bring up elemental species. So this is an area where Raman really excels compared to FTIR and GC. So all the various allotropes of carbon, such as charcoal, graphite, graphene, different kinds of carbonaceous materials that are inorganic in nature, they can be detected by Raman very well, but FTIR and GC will not see anything. The last point I want to make, which is a really important point, is about detection limit. So FTIR and Raman have a similar detection limit, 5 to 28%, and it really depends on the matrix, but that's kind of a general guideline. So they're not particularly sensitive. In contrast, GCMS is orders of magnitude more sensitive and can detect very trace species, down to hundreds of parts per billion. Now I want to bring up our newest technique. It's very useful for looking at really small features, and that, of course, is nano-IR. So here I have an illustration of how we employ nano-IR. Nano-IR is, as I mentioned before, has really the smallest spot size. And so here we have a multi-layer film. It's we didn't really know what it was, and turned out that it was a nylon film that has an ethylene vinyl alcohol in between. And so then we can see that, the two layers have different chemistry. We can see the middle layer very clearly. In addition, we also get some height information and some topography information, because this is basically an AFM type technique. So very, very useful for small areas. Here's just an overall summary of the comparison between IR, Raman, and nano-IR. So, IR has the greatest spectral range. Nano-IR does have a portion of the spectrum cut off, but thankfully it's not the most important part, so we can still get a lot of great information. The depth of analysis, now you see here 50 nanometers for FTIR. This is because we actually have a special accessory called grazing angle accessory that allows us to get information from the very top of the surface. With Raman, it's just 1 micron. That's really the depth. And with nano-IR, we can get down as little as 30 nanometers. So really amazing. We can vary the spot size with FTIR from 20 to 100 microns, with Raman from 1 to 10 microns. And again, with nano-IR, we have a lot of options down to 30 nanometers. As mentioned before, we don't have a lot of information on inorganics, and I will say a little bit more about that in just the next slide. Raman is a bit better on inorganics than FTIR and nano-IR. And it's important to note that nano-IR is very similar to FTIR once you've acquired the spectrum. And so because of that, you get to use the extensive library of FTIR. FTIR has a library with more than 350,000 entries, which again can be used by nano-IR. In contrast, Raman has a library of about 30,000, so about an order of magnitude less. And that's why for any kind of unknown material, if we have enough material, we always like to start with FTIR because the libraries are just so great. Okay, so I'm coming to the end, and I'd like to talk about inorganic materials. As I mentioned before, these spectroscopic techniques are really wonderful for organics. They have really beautiful, rich spectra. But there are some inorganic molecules that can be detected by these techniques. So with FTIR, we can see certain inorganics, particularly we can see carbonates really well, nitrates, sulfates, and silicates. The problem is that they are not always very specific, and we don't know. It would be very hard for us to tell the difference between, let's say, a silicate and a sulfate, because they all have a peak around 1,000. So these work really well when they're coupled with an elemental technique. such as EDS, XRF, XPS, or others, some of the techniques that were just discussed before. If they are coupled together, then you really can understand what's going on. But if you just have FTIR alone for inorganics, you might be confused. There is one special case where Raman really, really shines compared to other techniques. First of all, it can also detect carbonates, nitrates, sulfates, silicates, metal oxides, very good at metal oxide, and specific ceramics. It's very good for crystalline materials. Again, crystalline materials have a lot of symmetry, and Raman really kind of feeds off that. But this one special case that I want to mention is dealing with rust. Okay, so Raman, as you can see, can detect all these various forms of iron oxides and hydroxides. So if you suspect that you might have rust, this is probably the best technique to check because it has a very, very specific, very clear signature. And while an elemental technique, it will tell you have iron and oxygen, it might not tell you the bonding the way that Raman is. So to conclude, inorganics can be detected with our spectroscopic techniques, but they work much better when they're coupled with an elemental technique. And with that, there are some questions. Can these techniques can be used to identify organic residues? Absolutely. They can also be very useful for looking at different components of the battery, such as a separator, the binder and the electrodes, and so on. We can also do experiments to identify the type of adhesive, and even in some cases determine the degree of cure of that adhesive. There's also a special application of these techniques, specifically FTIR, looking at SiH and NH bonding in thin films. And this is actually one area where we can be quite quantitative. And of course, anytime you have contamination analysis, that's when you don't know what you have, right? You don't know what the contaminant is. A great place to start is with these techniques that I just mentioned. And with that, I'd like to pass it on to my colleague, Stephanie Williams.
Thanks, Yannicka, for the introduction. So, like you said, my name's Stephanie Williams, and I'm going to be talking about the X-ray diffraction and how that ties into our materials identification. So first, we're going to talk about X-rays. X-rays are, and I know I'm a little biased, but they're one portion of the electromagnetic spectrum, and we use those X-rays in a very interesting way. And I promise this slide is the only math you're going to have to look at, but I really wanted to discuss diffraction and why this is such a powerful technique. So here we have a crystal lattice structure, and what these are planes, and these dots are basically symmetrical repeating nodes. They don't have to be atoms, but essentially you have long range order, and the distance between these planes of repeating structure are called the distance is called the D spacing. Now, what we do is we introduce X-rays, and the X-rays come in and then they diffract out. And you'll see here that this is a 1 wavelength long. Now we add a bunch more X-rays. The fun part about this is that if you continue these lines down here, we can mark and see that for each increasing D spacing, you add half a wavelength to both the incident and diffracted side of the beam. So there's a half here and a half here. Now there's a full wavelength here and a full wavelength here. If you continued these lines down and then measured these wavelengths on the next D spacing down, there'd be a wavelength and a half on each side, etc. And what that means is that we can draw this triangle here and go back to our wonderful trigonometry from high school. And we call this angle theta. So this angle here is 2 theta. And with a little bit of SOHCAHTOA, we can work out this n lambda equals 2d sine theta, which is Bragg's law. So what that means is that if you have a repeating structure, you will satisfy these diffracting conditions. And these diffracting conditions is what gives you the peaks in an XRD spectrum. And really, that's the bread and butter of the materials identification, is the phase identification of crystalline materials. It's incredibly structurally sensitive. So here we can see a spectrum with a mixture of phases, but we can clearly see that there are 2 distinct crystalline phases. There's an aluminum oxide and a titanium nitride in the blue and red lines. Now we can do a little bit more than just identify phases. We can do a semi-quantitative analysis, where essentially you're analyzing the peaks under the area under the peaks, and then representing that in weight percent. You'll notice here that there's this very broad hump at a low 2 theta range, which is an amorphous material. And if we know the density of that amorphous material, we can also factor that into our calculation. And we can also give percent crystallinity if we take, again, we fit the profiles of the crystalline peaks against the amorphous peaks, and we see the percentage of the area that's representative of both. So this sample here is approximately 47% crystalline. And then the other thing we can do is that we can roughly approximate crystallite size, which is a function of full width half max of the peaks in each crystallographic direction, essentially. And so what we can do is we take an average of the approximate crystallite sizes in the most intense, least overlapped peaks. So these are some approximate crystallite sizes for the 2 crystalline phases in this sample. So I also wanted to touch on XRR. So which goes hand in hand with materials identification. When you do know the identity of the material, XRR is very powerful for thin films, which is another technique that, like Monica was talking about earlier about thin films and analyzing thin films, we can determine 3 things from XRR: density, roughness, and thickness of a thin film. And we can model usually out to 3 or even 4 layer models of films. And really this critical angle is where this intensity drop off is. And depending on where it drops off is whether your material is more or less dense. The slope, whether or not this drops down very sharply or is a very, shallow slope. This would be a very smooth sample. Dropping very sharply would be a rougher sample. And then the fringes, the frequency of the fringes, if there's many small fringes, that means you have a very thick film. But if you have very large and very few fringes, that's a very thin film. So this gives you a lot of great information about what your film is and what it's comprised of. So this is just a picture of our lab, and then this is a close-up of one of our newer instruments that we're very proud of, and there's only 2 of these in the world as of the moment that I'm speaking about this. And we have instruments from Rigaku, Bruker, Panalytical. We have 9 X-ray diffractometers. We can do so much more than just material identification, but we can do, non-ambient phase identification. We can do some in situ and in operando modes. We can work on very, very small samples and very, very thin films. So we have a wide range of tools to solve really a lot of complicated sample problems. So this is my summary slide. The long story short, X-ray diffraction is actually a structurally sensitive technique. It's not actually elementally sensitive like some of the other techniques that were talked about today. And so what we really get to probe is how the material is structured and how the atoms are arranged in a long order. And then your XRR gives you a lot of great thin film information. And I just have a couple of seed questions here about, kind of summarizing some common questions that we get about X-ray diffraction. But a really great benefit of using XRD is that it's typically non-destructive, as long as we don't have to adjust or modify your sample to fit it into the instrument. The X-rays itself are not going to actually damage the material. We use a software called JADE from Materials Data, and this is how we analyze and do all of the data analysis that I showed earlier on. We can go down to about 10 nanometers in terms of measuring film thicknesses. And we do have some minimal SAX capabilities, small angle X-ray scattering, which is, would be nanoparticles suspended in solution, or we could do some pore size analysis on some types of films. And when we're doing this phase identification and we're matching these phases, we're matching them against a database, and the database we use is through the ICDD, and our database has over 500,000 inorganic compounds and 500,000 organic compounds. So with that, I'm going to hand it off to John Mosquito.
Thank you, Stephanie, and everyone. Again, thank you for coming. This is going to conclude our talk, and so I want to close with just a couple last slides here. Last is to remind you why choose EAG. Really, there's a number of reasons why. First is client confidentiality. This is core to our business, making sure your information and your data is yours. That's what we do, and we take client confidentiality very, very seriously. We are established thought leaders in investigative science, meaning we are experts in the technologies and the materials that you bring to us. Use us as a resource, use us as a part of your team to help you move your projects forward. We have extensive knowledge base and skilled expertise. We have the questions you might have, we've probably seen it. We will help you determine the right techniques, the right analytical tools, and to get you the information that you need, and to help you interpret that data also. This is part of the service that EAG offers. We can offer a multidisciplinary approach to support you, meaning, as you saw already, we have many, many analytical tools. We have deep knowledge. We can help you choose the one right technique to answer the question that you have, potentially answer this next question and the third question all at the same time, and also help you interpret. If that's not enough, we can lay out a plan of attack to answer your questions and use multiple techniques to build that data set to give you the best answer possible. And we can scale with your demand and meet your time constraints. We own many, many instruments. We have very quick turnaround. We are a global leader in materials testing. We look forward to working with you. We know how to solve your materials and engineering related product problems. We can help you be the solution. We look forward to speaking with you privately. And I'd like to just finally close with a picture of our smart chart to again remind you of the techniques that we've covered during this conversation. They're listed here in orange and in blue to remind you of the ones, but we do have many other techniques. We're going to be having more of these coffees and conversations through the rest of this year. I hope you're able to join us for those. And if you'd like a copy of the smart chart, there is a QR code here in the bottom corner. Please use that. Use your smartphone. You can click on that. If not, you can go when you go back to your offices. You can come on to our website at eag.com and order your smart chart there also. Again, thank you all very much for attending, and we look forward to seeing you again very, very soon.